Hajra. He's from Institute of Mathematical Sciences at Chennai. So he will be talking about CMB data, a discussion on physics and systematics. Yeah, Dheeraj.
Hello, can you hear me? Thank you, Anjanda. Good morning, everyone. First of all, I would like to thank the organizers for inviting me here. And well, when I wrote to Devotam regarding what do you want to hear from me, I had three topics in mind. One was inflation, one was reionization, another was CMB data in general. So he asked me to talk about CMB data. So the CMB data that I'm going to talk about, it's like a general overview based on some of my earlier and recent works. So it is not based on a particular topic like inflation or reionization or anything, but mainly the talk is divided into three parts. First is joint estimation, where I'll talk about how CMB data can constrain models and how other data sets, other observations can complement in constraining models. And the second part, I'll talk about new physics, whether we can get new physics from data, etc., from the anomalies or tensions, anomalies within the data and tensions with other data sets. And the third part, I'll talk about systematics, and that is my plan. So I'm not going to spend even a minute for this one, just to tell you, because we have seen at least 4 times this picture yesterday, and CMB is coming from here, which is 380,000 years after the Big Bang. Well, before going to joint estimation, this is the standard model. Whenever you are trying to constrain a model or you are trying to understand the physics, you have some basic understanding of the system. For example, here the system is our universe. You can, you know that from observations that we have a homogeneous and isotropic universe. Based on that, you work out the Einstein's equations of general theory of relativity. And from there, you can understand that there are some certain relevant parameters that you need to work with. And you build a model, and that's what we call standard model, and plus some ingredients for a particular analysis, including some ingredients for a particular analysis. We call it a baseline. Well, standard model and baseline are sometimes considered together, but baseline has certain properties that baseline refers to an analysis or for a particular observation on which the standard model is compared with. For example, standard model is lambda CDM, but baseline has few other properties like neutrino mass. You could put it to be 0, but here it is. We are using it as a 0.06 electron volt, etc. The effective relativistic species is considered to be 3.046, etc. So together these things we call it a baseline model. Okay, and this baseline or the standard model has 2 ingredients. One is the background part, which is called lambda CDM, and the second part is the primordial power spectrum, which we consider to be power law. Okay, it is a 6-parameter model, of which 2 parameters are actually responsible for the energy budget of our universe. One corresponds to the baryon density, and one corresponds to the cold dark matter density. If you are not varying the curvature, you are saying that the universe is flat, then the dark energy density simply comes as the rest part that is not covered by the baryon and cold dark matter. And one parameter corresponds to the expansion rate today, which is the Hubble parameter today. One parameter corresponds to the optical depth, tau. All right. And 2 parameters are there to constrain the to describe the initial condition. And these 2 parameters are one is AS and another is NS. As I said, in the standard model we are calling it as a power law. The primordial power spectrum, we are considering the power law to be the shape of the primordial spectrum. And therefore, if you have a power law, you can constrain it by you can describe it by 2 parameters. One is its amplitude, and another is how much tilted it is, okay? So till now we have been able to constrain this very well, and these are the most recent. Okay, this is the Planck PR3 analysis. There has been some other N-pipe PR4 analysis. So, but it is the most recent official release of the Planck data. So this is the temperature and isotropy data. Here you can see that this is the standard model, and these are the residuals with respect to the standard model. This is TE and this is EE. So this is temperature and polarization cross correlation, and this is polarization autocorrelation. And you can see that the standard model is fitting the data exceptionally well at all scales. Of course, there are certain peaks and troughs, as you can see. Here they have certain varying significances. For example, here it is 3 sigma. There are certain 2 to 3 sigma significances. But overall, at all scales, power law and the lambda CDM, the standard model together, is performing pretty well. And these are the parameters, as I said. The first group or the first row group that you can see, it is this is describing the standard model, and these are the first 6 parameters I talked about, and these are the constraints based on different combination of the data. For example, temperature plus polarization autocorrelation, and then this is the full temperature and polarization, and this is including lensing, and this is including external data sets. So these 6 parameters are standard because if you are throwing away any one of the parameters, you cannot feed the CMB data. That is to be understood, that if you are, all of these are essential parameters. So you cannot do the CMB data analysis without any one of these parameters. Now coming to the main part of my talk. So, okay. Now, we have only one universe. So if you are trying to observe something with the CMB, and if you are trying to constrain physics, we have one universe, one physics. And if you are trying to constrain that physics, if CMB is constraining some part of it, other data sets can constrain other parts of it as well. That is the beauty of it. We can do joint analysis. And that is what you are seeing from yesterday's talk, that we combine CMB plus Hubble CMB plus large scale structure CMB plus other data sets, etc., Lyman alpha. So yeah, combining data sets that are not in tension, this is very important with respect to a model. So data, whenever we say tension, it is with respect to a model. Whenever we say anomaly, it is with respect to a model. Okay. So here the model in discussion is standard model. It provides stringent constraints on that model and can help to rule out other models that are there. Second part, anomalies and tensions between the data sets sometimes indicate new physics, but in most of the times they indicate unknown systematics. So let me start the joint estimation. So here for joint estimation, I have taken some of my works on reionization. Reionization is mainly constrained from the CMB part. It is the parameter of the reionization that is constrained mainly is tau, the optical depth. It is the integral of the electron fraction along the line of sight. Okay, so the CMB photons get polarized with the free electrons that are there in the universe after the reionization or during the reionization, and we find its imprints in the E mode polarization and at the very large scales or the very low L around here. Okay, now so reionization is not just about tau, the integral. It is about the shape as well. When the reionization started, when the electron fraction was 10%, let's say, and it became 100%, when the universe transited from a neutral state to an ionized state, the whole history is called the reionization history. But CMB cannot say much about that apart from the optical depth. Main reason is that if the reionization history is extending to higher redshifts, we can differentiate between histories. But If it is a very short-lived reionization and happened at a very recent epoch, let's say between redshift 8 to 6, then your imprints will be here only, and you do not have much area to play with, because here you are basically dominated by cosmic variance. It is a statistical uncertainty that is there in the CMB. Even with the cosmic variance limited CMB polarization data that we are expecting in future from LightBird, we will not be able to see this kind of, we will not be able to see reionization histories beyond certain limit with CMB. So we need other data sets. Since WMAP, we have witnessed a decreasing trend of optical depth. For example, this was the WMAP first year data and then last year data. And with Planck, you can see the tau value or the optical depth value changed from nearly 0.1 to 0.05. Okay, now the value is 0.054 plus minus 0.007. And the reason is this. So this was the Planck 2015 release, and this was the best fit from the Planck 2018 release, and you can see that the amplitude decreased. That is the reason for the decrease in the tau value. Okay. Now, whenever we are trying to constrain the reionization history with CMB, what we do is that we just take a ad hoc model, a tan hyperbolic model, a near symmetric model, which says that the electron fraction has increased from the low redshift, for the high redshift to the low redshift in a tan hyperbolic manner. So it goes from 0 to 1 in a tan hyperbolic manner. But actually, it has a physics behind it, and the physics is this, that you have to solve the ionization equation, which has a source term that contains, sorry, this should be here. This has a source term and a sink term. And the source term says how much ionizing photon are there, and the sink term is saying that what is the recombination rate or the recombination time. I'm very sorry for this mix up. The source term, this should be here. Okay. So in our work here, we had given a general prescription saying that we do not have to make any assumption about the source and sink term. We keep it completely general and we reconstruct the ionization history, and we take different combination of the data. For example, Planck and UV17, Planck and QH2, QH3 data are basically neutral hydrogen data or the ionized fraction obtained from quasars and different other surveys, okay, Lyman alpha emission, etc. Here I just picked up one particular plot which is very important. This is the ionizing efficiency of the photons, and this is the tau value. Okay, as you can see that with Planck and UV17, they have this contour. You can get this contour, and with Planck plus QH2, which is the neutral hydrogen data, you can get a constraint which is perpendicular to this. So when you combine them, you get something, a contour that is, I mean, this is not in tension, but they are actually having two different degeneracies, degeneracies in two different directions, which is beautiful, and that is how you get stringent constraints by combining the data sets. This is like what when you were seeing with the supernova data and BAO data and CMB data when we were constraining omega matter and omega lambda when you varied omega k, the curvature density, right? And it is similar to that when you have joint estimation, you can get stringent constraints on the parameters or the physics, and this is what we had obtained from a free-form reionization history constraint, and we found that tau is nearly 0.051 plus minus 0.001, which is 2 times better than a cosmic variance limited observation. Okay. Now we try to see whether we can actually say more about it using the combination of the data. I said that in CMB we use this value, we use this form tan hyperbolic for explaining reionization history. But let's say we try to see whether this is actually supported by the data or not. Of course, it is supported by the CMB data because CMB data cannot see anything beyond tau. Mostly it cannot see anything beyond tau. It's blurry. But combining with other data sets, can we say anything about the symmetry of the ionization history in redshift? Okay. So what we did is that we worked on a simple mathematical formula, and we said that the reionization for a symmetric model, we are basically saying it as 1 plus error function, which whose derivative actually gives you a Gaussian profile, and we said that the skewed normal distribution is represented by this. This T is Wiener's T distribution, and it has only one extra parameter. So if alpha is equal to 0, it is a error function which is symmetric, perfectly symmetric, close to a tan hyperbolic. But if it is not, then it gives a skewness to your distribution. Okay. And you compare, and you basically you keep on adding the data set. So this is the alpha parameter. Okay. Forget about all the other parameters, tau or the delta z, reionization, etc. Forget about everything. So we are allowing everything to vary. But when you are using Planck, you cannot say anything about the symmetry. Okay. There is a little bit improvement with asymmetry, but improvement in fit, maybe 1 chi-square or 2 chi-square, but not much. Planck plus QH second, which is the neutral hydrogen data, it also does not say much. Planck plus UV17 data also does not say much. But if you combine them together, it actually rules out a alpha equal to 0 by more than 4 or 5 sigma. It depends on what Lowell data set that you are using, but it is of the order of 5 sigma or something like that, and I think 4 sigma, okay, 5 sigma I shouldn't say, and we are getting very good base factor as well. And so what we are seeing here, that using a joint estimation from Planck and other data set, so this UV luminosity is basically from the Hubble Space Telescope. So when you combine these data sets, you can actually say that no, our reionization history is not symmetric, and the data set or the observations actually prefer an asymmetric history of ionization, and that is why if you use that model, you will get a biased result. Okay. So the prescription what we provided is that you should use a model like this which includes asymmetry. Now when you solve the reionization from simulation, etc., you never get symmetric history, but this is a proof that the data does not like the symmetric model as well. Okay. No, there is no fundamental reason. The way, as I said that you have this UV luminosities that actually those are the galaxies or the stars that are ionizing the universe. Now it is possible that with a very the luminosity density is varying with redshift in a particular manner. Okay. Now in order to have symmetric histories, you need a luminosity density varying in a particular in a different manner, which is not supported by the data. Of course, here when we are doing it, you see that this is the for alpha equal to 0 we are getting symmetric, right? So what we do is that we basically reverse engineer what can be the UV luminosity. Okay. So we find that whenever you see, if you, okay, I did not add the plot. So the UV luminosity data that we have from the Hubble Space Telescope is not at all agreeing with the shape that you can find only from the symmetric histories. So there is no fundamental theory. If it had been like that, would have been fine. Yeah. Okay, now I am coming to the new physics, the second part. Okay, so to begin with, so to begin this part, I took the liberty to say show a photo that is a treasure to me, and since this is this today is we are celebrating Starobinsky Memorial Lecture as well. We are having a Starobinsky Memorial Lecture as well. This photo is a gem for me, and it was taken at APCTP, Asia Pacific Center for Theoretical Physics. I was a postdoc there with Arman, and we started working on models which later came out as whipped inflation, weakly whipped inflation, and we started working on different aspects, primordial black holes, dark energy, etc. So yeah, so I'm not going to talk much about that. So just one slide on one of our models, weakly whipped inflation, with the recent data sets that came out in 2021. So I showed you that these residuals with respect to the standard model, right? And the standard, so there can be some hints from new physics from these residuals. For example, if you have discontinuities in the inflation potential or in the derivative of the potential, that leads to violation of slow roll because the scalar field is going to jump around, and you get oscillations in the primordial power spectrums, therefore you get oscillations in the angular power spectrum as well, right? And that gives you, so this is the primordial power spectrum, this is the angular power spectrum, for different choices of the potential and different choices of the parameters, and these are the local best fits to the data. And then the residual for high frequency oscillations and low frequency oscillations that are favored by the data are this, okay? It is, so weakly whipped inflation was a single field model. Recently we have worked on a multi-field model where we solve the multi-field model exactly, and you can find certain similar, not very similar in analytical form, but these are actually anyway numerically computed. But we are finding that there are certain oscillations that are favored by the temperature and the polarization and their cross correlation, okay? And this has a frequency of 18. So it is basically the heavy field mass is of the order of 18 m sigma, which is the heavy field. M sigma divided by h is basically 18, and that is what we find as the oscillation frequency in the primordial power spectrum. So these are the different oscillations, and these are the residuals, okay? And you can see that they're fitting it well. Anyway, so these are the cases where anomalies in the data can hint towards new physics. Sometimes tensions between the data sets also lead to some new physics. In history it had happened, and for example, you know the discovery of dark energy and the dark matter as well, okay? But anyway, so here what we are seeing is that we try to project the tension, okay, cosmological tension in the initial condition, and this is the power spectrum that we got. We call it one spectrum, and this power spectrum, just if you feed it to the CMB, you get of the order of 9 to 10 improvement in fit, and this comes with lower S8 and higher H0. H0 is not as high. We can get it from 67 to 68.5 or 69 at most, but with H0, addition with H0, we can get it up to 70 or 71 at most, but not more than that. So it reduces the tensions, but it solves some anomalies in the CMB, okay? And this is the slow roll modification that if you try to project it in the slow roll parameters, okay? Anyway, we are not solving with any slow roll approximation. This is with complete numerical analysis. We are solving the Mukhanov-Sasaki equations. So yeah, so we have 2 papers on this, and this is the potential, the fraction of change in the potential that you need with respect to any baseline potential. So here you can use m square phi square, or any n square phi square is ruled out, but anyway you can use any small field potential or Stravinsky potential. You can add this part to it, and it can generate a feature in the primordial power spectrum like this, okay? So this is the last part of my talk. Here I talk about the systematics. So here are a few examples of the systematics, historical examples of the systematics that we had from the beginning of the Planck first year data. So there was this 2.5% amplitude mismatch between Planck 2013 and WMAP release, okay, which is a huge, because all of your most of your parameters will be off this amplitude, and therefore the tau because of their degeneracies, etc. There was a 217 gigahertz systematics because there was a problem in the 4K cooler, and that gave certain oscillations at the small scales. Planck PR3 systematics in the lensing, we call it lensing anomaly. And Anjanda, how much time do I have? 5 minutes, okay, good. And we also have seen BICEP2, the famous BICEP2 dust polarization. Many of us worked on that, and we thought that it is a signal, and also proposed theoretical models of inflation that can reduce the tension between the Planck and BICEP2. But anyway, it came out to be dust polarization, which was heartbreak for many of us. And recently, ACT DR4 systematics. There has been something in between this SPT systematics. SPT wanted some higher spectral tilt, but finally they found that it is not there. And then, in the next release, they had a result that was matching with Planck very well. So systematics come and go, okay? So sometimes systematics come in the way of the accurate parameter estimation, that your parameter is off or something like that, and sometimes they can falsely hint towards neophysics. This is not much of a risk, but this is a huge risk. So and I'm going to talk about this Planck and ACT systematics in more detail now. But before that, let me just show you the amplitude mismatch between Planck and WMAP. So this was the Planck data. This is the WMAP data, and Planck best fit and WMAP best fit. As you can see, there is a mismatch. I am not plotting the data here, Planck data here, only the WMAP data. But you can see that the best fit have a mismatch. Okay. And if you see, we did an analysis, and where we are modifying the WMAP best fit with certain functions, and we are trying to see that where the problems lie. We found that the problem doesn't lie here only, the 2.5%, but problem lies here as well. All the WMAP was not there, but its best fit can extend, we can extend it to, because it is a theoretical model, we can extend it to small scales as far as Planck go. And we compared the model, and we found that these are the MC-MC chains, and this is the Planck best fit, WMAP best fit versus Planck chains, okay? And you can see that this is the 2.5% and the excess scale dependent mismatch as well. And this is the comparison of the concordance model and Planck. We found that actually you need a suppression in the angular power spectrum, and this need is generated by the Planck data. And then finally we found that if you remove the 217 gigahertz to 207 and cross 200 gigahertz auto power spectrum, thanks to Professor George Stathiou, who pointed that do the analysis without this one, and then we did it, and we found that it actually this suppression goes away, and that was actually coming from this 4K cooler systematics in the Planck observation. And as you can see that if the systematics was there, it was not removed in the later releases, we would have still thought that a suppression is there, and we would have thought that okay, maybe it is a neutrino mass or some running in the primordial spectral indices, primordial primordial spectral tilt, etc. And we would have thought that okay, this might be hinting towards a new physics. But anyway, luckily Planck also removed the systematics in the 2015 release, and it was gone. This is the ACT DR4 analysis and Planck analysis superposed together, and you can see I'm just going to show you this NS, the spectral tilt, and this shows something like 3 sigma discrepancy. So this is the Planck analysis, and this is the ACT DR4 analysis. So ACT DR4 actually wants a value which is 1.008 and Planck wants a value 0.96. Okay, and they showed that if you fix the amplitude obtained by Planck at L equal to 220, it removes the systematics. But if you do that, you will see that there is a worse fit to the data, okay, to the ACT data. Also, they showed that ad hoc scaling, if you scale the temperature polarization cross correlation by 5%, you can remove this systematics, remove this discrepancy. But anyway, why would you ad hoc scale the spectrum, the data in an ad hoc way, right? So we tried to understand the mismatch in this paper, and there has been many papers. For example, Anjunda yesterday talked about early dark energy model, and there was a paper saying that if you take Planck up to 650, I think there were 2 papers, and Atacama Cosmology Telescope after that, then you say you get a 3 sigma confirmation of the early dark energy model. Now I'm going to show you what happens for other models also, okay? So I take a very simple approach on this, and I say that, okay, I have a tilt mismatch, let me work with a tilt. A large scale we have a tilt, and a small scale we have a tilt. I'm not saying at what scale which tilt will be there, I'm varying everything, okay? And I say that there is a break point, so my primordial power spectrum is not like this, but it is like a broken power spectrum like this. And the break point happens at K break, and amplitude is defined at K break, and it has 2 spectral indices, NS1 and NS2. Very simple thing is that if you get NS1 minus NS2 minus NS1 is not equal to 0. I need 2 minutes, I will finish. Thank you. Yeah, not equal to 0, then we find the discrepancy, okay, or new physics or something like that. And you see, if you add ACT and Planck, but you take Planck up to 1800 and ACT after that in the temperature, and take the full polarization of ACT according to their signal to noise ratio, respecting their signal to noise ratio. So I'm saying that I am taking Planck till the point where Planck is better than ACT, and I am taking ACT after the point when ACT basically surpasses Planck, okay? There is the delta NS is 0. There is no significance, a little bit there, but nothing much. If you restrict your analysis with Planck 100 gigahertz, L less than 650, the way this dark energy signature was there, you find a discrepancy, and this is like delta NS is nearly 3 sigma or something like that. If you remove the Planck temperature altogether, just use ACT, you get really very good significance, and this is the base factor. So what we find is that if you combine Planck and ACT by respecting their signal to noise ratios, you do not find any significance, okay? But if you act them in a special way so that your model is favored, then you find something like 9 improvement or 10 improvement in fit by this new model, and you can falsely find a hope for a new physics. But here it is important. So systematics you will never be able to understand unless you are actually understanding the foregrounds very well, or what is going wrong with your experiments, okay? And but this is the most we can do, that we can try to understand, break the data in different segments, and we see that there is a varying significance for our new model. So the significance is 1.2 or 1.8 here, which is substantial, but this says that the significance is varying as you change the data combination. That means that it is not a new physics. It is strongly strongly hinting towards a systematics. We did the analysis by reconstruction as well. This is the Planck reconstruction. This is a direct reconstruction of the primordial power spectrum from the data. So this is the NS. So this is the NS that you can see. This is the Planck NS we found, and this is the ACT NS. Okay, the purple line. It is shown purple. Yeah, it is purple anyway. So this is the ACT best fit, and this is the Planck best fit. Planck reconstruction shows that the Planck best fit is actually doing very well. So it is within the 1 sigma of at all scales. Okay, Now we do Atacama Cosmology Telescope reconstruction, and this is what you find. Actually, there is a tension between within the Atacama Cosmology Telescope itself, that it is preferring the break of the power spectrum at 2 sigma. This means that basically you are saying that there is a change in the spectral tilt, okay? And as you go towards small scales, and we found that around this scale only the spectral tilt comes down to, it deviates from 0.96, it goes towards 1, okay? This is where you find. So we found basically that the disagreement between the data, between the Planck and the SGT data exists between 0.08 to 0.16 megaparsec inverse. Okay, so this was a systematic, and we do not know the reason for the systematic, but we very well know that it is within Planck. Our analysis also hints towards that. So I just write the same things that I started with. Joint estimation, new physics and systematics. So just a note to leave you with. You have to take all these into account when you are doing a cosmological analysis with the data with your preferred model or even the standard model. So with that, I would like to stop. Thank you.
Thanks, Dheeraj. So for lack of time, we can take 2 questions. So yeah.
Thank you, sir. A very good talk. So I am asking from a theoretical point of view. You have taken the 2 spectral indices, and it is a breaking point of the power spectrum. And you talked about systematics. But I am asking that for inflation, like when we do the typical Jeans calculation itself, we get Harrison-Zeldovich spectrum. We know the scale invariant power spectrum. So I am asking that from a theoretical point of view, what would explain the 2 spectral indices? I mean, is it the scalar field is getting a phase transition? Or because I believe that both of them are in very high redshift, both ACT and BR. So could you tell like what physics would be included to explain theoretically that the 2 different spectral indices? Thank you.
Okay. So one thing is that we do not get Harrison-Zeldovich, we get 0.96 from inflation. No, we expect nearly scale invariance. Like even if you take m square phi square, you get 0.97 or something like that. Okay, and yeah, so you can generate this type of spectrum. If you want to tag it as new physics, and if you want your favorite model to come in, what you can do is that I can very simply cook up a model where there is a transition in the scalar field potential itself, that it is following a power law. Let's say m square phi square, and next time it transits to a like lambda phi or lambda phi 4 kind of thing. Okay, so it is a transition in the scalar field. There has been some works earlier. I mean, Starobinsky had the initial work in 1992, but afterwards people showed also that there can be like a tunneling effect. Okay, and I am not an expert. People talk about Coleman-Delucia bubble, etc., and where the scalar field tunnels, and there is a false vacuum, and so the scalar field have one potential and transits to another potential, and with a continuous transition, and that has the first potential gives you the first large scale tilt, and the second potential gives you the small scale tilt. You can get this type of thing. You can see our paper whipped inflation. So there we basically showed that the field is actually the potential is actually differentiable till second derivative, and so you do not have a problem of it is a smooth potential. The first derivative is continuous. Second derivative just has the second derivative is discontinuous, I guess. Yes, and you can get that. Continuity is preserved. What you see there is a very continuous transition at a very large scales. It starts with something like ns equal to 1, and it translates. Goes to ns equal to 0.96 afterwards. This kind of thing.
related to the fact that when you're talking about this optical depth and there is asymmetry in the alpha membrane,
Yes.
I think. So how much it depends upon how you model your asymmetry? I mean, is it like you have a sort of error function and then take a T distribution? Right?
Yes.
So if I take any other defined distribution than T, that actually model your asymmetry. So how much that depends upon your modeling the asymmetry?
We did not try any other model because this is the simplest function with one parameter extension. You can go with other function as well. You can get different result maybe, but we are showing that we just
alpha is peaking at some point at non-zero values.
yes.
So how that result depends upon your model, I mean like modeling the asymmetry.
Yeah, I found that this with error function, the extension, I mean, you start with a Gaussian, and the simplest one is this ONC distribution that actually incorporates Gaussian as a limit of alpha equal to 0. I mean, there must be other functions. Maybe the significance might vary that at what, let's say there is a alpha prime in a different model, at to what extent the symmetry is broken by changing the alpha. So you can get, I think.
One question is it stable? Like,
okay. I didn't test it, but I think it should be stable. The only thing is that in that model, your alpha value is going to be, it will be changed, okay. But you will still get something like 3 or 4 sigma.
Okay, so let's thank Dheeraj again. So let's go to our next speaker. That is Dr. Indrani Banerjee from NIT Rourkela. So she will be talking about prospects of considering the nature of strong gravity from the EHT data.
Hello, hello.
Okay, so good morning all. Before I begin, I would like to thank the organizers for the invitation and also for giving me this opportunity to present some of our works here. So today I will be talking about the prospects of constraining the nature of strong gravity from the Event Horizon Telescope data. So as we all know, GR is a very successful theory, I mean the most successful theory of gravity, and it has passed all the weak field tests, particularly the perihelion precession of Mercury, bending of light, the gravitational redshift, and even in the strong field regime, if we are studying the electromagnetic emission from the accretion disk and also the gravitational waves, GR is very much consistent with all the data, even the strong field. So, and particularly the images of black holes, the image of M87 star and Sagittarius A star, which I will be discussing in this particular talk, GR is also consistent with this. But still, we are looking, we need to understand whether GR is a good theory in the strong field regime, particularly because it has some issues in explaining the dark sector, the dark matter, dark energy, and also it is fraught with singularities, the black hole and the Big Bang singularities. So that is why it is important that we look for other alternatives to GR which can possibly give resolution which are not only address all the observations which GR can successfully explain, but also address one or some of these issues. So before going into any particular model, I would like to try to address what the data has to say. So this image is the first image of the black hole. So this is the image of M87 star, which is the black hole at the center of the elliptical galaxy M87. And this data was released on 10th of April 2019. And following this, 3 years later, the EHT released the data of Sagittarius A star, which is the black hole at the center of our Milky Way galaxy. Now, actually, one might wonder that why probably people would try to get this data, Sagittarius A star, before M87, because it is much closer to us. But the problem is that the solar system is in the galactic plane, in the Milky Way in the galactic plane, and also the Sagittarius A star is in the center of the galaxy. So there is a lot of dust extinction. So that is why to image this particular object, although it is nearer, was much more difficult. So the images were taken, the data was taken in 2017. But to release the data of Sagittarius A star took much longer time compared to that of M87 star. And you can also see that the image is much clearer in the M87 case compared to that of Sagittarius. So what is a black hole shadow? So when light from a distant astrophysical object, or maybe the electromagnetic emission from the accretion disk, it reaches us and it gets the black hole on the way, there is a strong gravitational bending of light. The shadow consists of the set of directions in the observer sky which just escapes the event horizon. That is why it can reach us. And it is the boundary of this particular object marks the light that can just reach the observer at infinity. So it testifies the signatures of strong lensing. So now how we came to imaging. So before the EHT era, all the data was in this. People were trying to model the stars around the black holes and study the electromagnetic emission from the accretion disk. And then came the gravitational waves. The data started coming up from 2015. But detecting GW, the gravitational waves was also like hearing black holes. And people were even more ambitious and they wanted to exactly image the event horizon. So this was actually very difficult because these black holes, although they are gigantic, they are very, very far away. And therefore, it requires telescopes of very high resolving power to get those images. So to get an estimate of the numbers, let us see that whatever we see in the observer sky is a shadow like this, and this object, the black hole, is at a distance of d from the observer. Now we can see that from simple geometry, we know that this angle delta is very, very small. So this delta, if delta beta by 2 is the radius of the shadow, then this radius scales with the mass gm by c squared, that's the gravitational radius, and also divided by the distance gives us the angular diameter. If we simply put in the numbers for a supermassive black hole, it is 1 billion times the mass of the sun, and if it is located at a distance of 1 megaparsec, we see that the resolution is 40 microarcsecond, the angular diameter. Compared to a stellar mass black hole, if it's a 10 solar mass black hole and you put it at 1 parsec distance, although the nearest stellar mass black hole is also like 478 parsecs, it is much smaller. So that's why it is easier to image a supermassive black hole, and hence the target was M87 star. So now we have already seen in the last slide that we need telescope resolution of the order of 40 microarcsecond. And then what kind of wavelength? Because the resolving power of a telescope depends on the wavelength. Now this wavelength, it turns out that it is the optimal wavelength is 1.3 millimeter, and that comes in the radio band. That is because, so first of all, the light which is emanating from near the event horizon, that should interact minimally with the accretion flow, because otherwise if there is a lot of scattering, then the image won't be very clear. Second thing is that it will pass through the interstellar medium, so there should also be minimal dust extinction. And finally, when it should be also transparent to our atmosphere. So the wavelength which satisfies this criteria turns out to be this 1.3 millimeter, and that is in the radio band. So if we put this 40 microarcsecond here and the wavelength around 1.2 millimeters, it turns out that it requires a telescope of the size of the Earth's diameter to get this kind of an image. And so this became possible with the advent of this VLBI technique, which is applied in this EHT telescope. So basically, Event Horizon Telescope is a network. In 2017, it was a network of 8 observatories spread around the world from Hawaii to Antarctica. And by 2021, 3 more observatories were added. So what they do is that each observatory, they target a particular object, for example, M87 star, and then each observatory looks at a certain part of its image. Okay, and then as the Earth rotates, they capture more and more segments of the same image of this object, and then with a lot of image processing, they come up with whatever is we are seeing here. And so the data was taken over 4 nights, and there were 4 data sets taken in 2017, and so it took 2 years to arrive at this final image. So 2 years, from 2017 to 2019, it took 2 years, and after a lot of data analysis and by using different calibration and imaging techniques, they unanimously came to the conclusion that this ring, the angular diameter of this ring is 42 plus minus 3 microarcsecond in diameter. So the ring is nearly circular. The central depression, one can see that there is a dark patch here, and that is surrounded by a ring. So the luminosity difference is like, the flux difference is like 10:1, greater than 1. So if it is 1 here, then it will be greater than 10 in the brighter region. One can also see an asymmetry. So this side is, the southern part of the ring is brighter, and that is often attributed to the relativistic beaming. So there is plasma moving at the speed of light, at nearly the speed of light around this object, and there is, because of this relativistic beaming, that is the part of the plasma which is moving closer to us has a greater flux. So that's why we see this asymmetry in the flux. And so this, a lot of, there was extensive GRMHD simulations were done, assuming that the metric which governs this particular, which is around this M87 star is the curved metric. So extensive GRMHD simulations tells us that the mass of this object is around 6.5 billion solar masses, and this is consistent with previous estimates of the mass of M87 star, which is around 6.2 billion solar masses, but that was by studying the motion of stars around this object. And so in 2018, the M87 star, so this same object was this data was released by M87 star by adding a new telescope in the EHT network. And it was found that the image size, that 42 plus minus 3 microarcsecond, is remarkably stable, but this brighter side of the ring, that has shifted by 30 degrees. Okay, so that is attributed to the accretion flow, but EHT team, they report that there are different, one can say that there are this whatever's and the angular diameter that you are seeing, that might be due to astrophysical effects, but that, for example, the emission blobs or due to jets or Einstein ring of the part of the jet which is on the opposite side, those things are actually, these are not astrophysical effects, but whatever the size of the ring that you are seeing is purely attributed to the background geometry. So this, and it's also proof of the fact that we have an event horizon. So this gives us an opportunity to, it's a direct evidence of the event horizon, and it allows us to also test GR and also constrain the other alternatives to general relativity. So now I again come back to this picture, this cartoon diagram. So one can see that how do we know about the background matrix. So I will soon in the next few slides discuss how one arrives at this kind of an image for this kind of a shadow for the black hole. So this shadow diameter, which is given by delta beta, that actually depends on the background space-time. If you are assuming that M87 star is a curved black hole, then you arrive at certain value of delta beta. So it depends on the spin, but the dependence on the mass is purely by scaling this particular thing. So you purely, suppose if it is set some value say 6, then you simply scale it with the mass and it is inversely proportional to the distance. So the information of the metric is there in this shadow radius, which we will compute with for the Kerr black hole in the, I will just explain in the next few slides. Also, it depends on how we are viewing the black hole. The inclination angle, that is also very important. So if you are viewing it from, say for example, if you are viewing it from the top, then we always see a circular shadow. But if you are viewing it at an angle, particularly if you are viewing it edge on, then it turns out that the shadow is non-circular. So the condition that the shadow is not circular, to get a non-circular shadow, we need both the rotation as well as the inclination angle has to be, I mean, high. I mean, more than it's, if we view it at 90 degrees, we will always get a dented shadow. So now to understand how to arrive at this, the dependence of the space-time, background space-time on the shadow, we take the example of the Schwarzschild solution, which is the non-rotating black hole in general relativity. Suppose we are shooting these photons. These photons are coming from different astrophysical objects, and while it reaches the observer here, it encounters a black hole. So what happens is that, suppose, so basically this is the impact parameter. So at a certain impact parameter, which is also which is called the critical impact parameter, one can show that the photon will simply go round and round this black hole, and the radius at which it will encircle this black hole for eternity is the radius of the photon sphere. Of course, this is the radial geodesic equation, and if one plots the potential in which the photons are moving, then one can show that this potential has a maxima. The moment you perturb this photon towards the, so inside, so at a radius less than this thrice of 3m, one can show that it will fall inside the black hole. If you perturb it out at a radius towards, so delta r is greater than thrice m, then it will reach the observer at infinity. So this is an unstable maxima, and if you shoot the photon at the critical, at an angle, at a distance, at the critical impact parameter, then one can show that it will simply go around this at the at this thrice m. The critical impact parameter is also the radius of the shadow. Whatever shadow radius we saw, this delta beta by 2, that is also equal to the critical impact parameter, and therefore this one can actually show, and this is this 3 root 3 times gm by c square is the characteristic of the background space-time, in this case the Schwarzschild. Now what happens if we, because astrophysical black holes are rotating, so we should work with the Kerr solution. Therefore, if we have a Kerr solution, so this is our Kerr metric, and we again focus on this radial geodesic equation of photons moving in the Kerr background. In this case, we find that there is not a single radius, I mean there is not a single photon sphere at which we have these unstable, the photon will just go round and round, but we have a photon region. So basically the situation is something like this. Suppose A equal to 0 is the Schwarzschild scenario, and then we have the photon sphere is at r equal to thrice m. But now if we just make the spin to be 0.1, we find that the photon region extends from say 2.9 to 3.1. The moment you increase the spin further, the photon region goes from 2 to 3.7. So there is a photon region, there is not a single one photon sphere at which the radial potential has both r dot equal to 0 and r double dot equal to 0. So that doesn't happen. The other thing is that at a given radius, so there is a range of radii which denotes the photon region, and at a given radii, it will just, this is the kind of motion the photon is executing, but that is at a given region, at a given r, and there is a range of r here. Okay. The other thing is that I have talked about the two L and eta in this radial potential in which the photon moves. This L and eta are the two impact parameters. So impact parameter, because in the Kerr case there is a chosen axis of rotation, Therefore, there are two impact parameters. One denotes the distance from the axis of rotation and the other is the distance from the equatorial plane. So, L here tells us about the impact, it is the impact parameter which is the distance from the axis of rotation, and eta tells us about how high it is above the equatorial plane. The photon cannot reach the pole in general. It is confined in a photon region, and also it cannot reach the pole. That actually comes from the condition of the geodesic equation in the theta direction. So we need to have this theta potential, not only the r but also theta potential, which also has to be positive. So these considerations actually dictate what kind of motion the photon will execute in a particular space-time within the photon region. Now, how is all this related to the shadow? So basically, this is, here we are the observer, we are at a distance d denoted by the blue dashed line. Say for example, the black hole, the rotation axis of the black hole is denoted by this blue dashed vertical line, and the photons, they are coming, the photon from this light source is coming, it reaches us, and there is a strong gravitational bending of light here. So whatever motion the photon is executing in the photon region, and it reaches us, because it's an unstable photon region, therefore all this motion is projected onto the observer sky. So the observer is viewing the black hole at a certain inclination angle, which is theta. Okay. Now that is, this angle is taken with respect to the rotation axis of the black hole. So we project the motion, or whatever motion the photon is executing, onto the observer plane. So the xy plane is denoted by the observer's plane or the observer sky. So this is actually perpendicular to the line of sight. So we project the motion of photons onto this plane, and what we arrive at is this 2D curve, which is the black hole shadow. So I will not get into the details of how you arrive at it, but one can show that the x and y coordinate of the shadow, that depends on the two impact parameters that I discussed a while ago. So in these impact parameters, on the other hand, they depend on the metric. So that is how the x and the coordinate, the delta beta or whatever the diameter of the shadow, depends on the background space-time. But one has, so basically we have a parametric equation. We need to get a curve, we need beta in terms of alpha. But we have this r here. The r is the radius of the photon region. So we have to eliminate r from these two equations. It is much like the fact that the parametric equations for a circle. We have x is equal to a cos theta, y equal to a sin theta. We eliminate theta to get y as a function of x. So similarly, we have to eliminate this r from these two equations to get beta as a function of alpha, that is the contour of the shadow. So basically, so now one can see from these equations that whatever the functional form of L and eta, that is characteristic to the space-time metric. Here the curve metric. The spin is already here. Also, one can note that the inclination angle, the angle at which we are viewing the black hole, the angle it makes to the axis of rotation, that also comes here. Okay. So if the black hole is observed, even if it is rotating, if the black hole is observed face on, we are directly observing along the axis of rotation, then we will always see a circular shadow, but the radius, the diameter of the shadow will depend on the spin. But if we are seeing it more and more edge on, we will see that this is not the shadow will no more be a circle, but it will be dented. So with this, so dependence, we have now seen that this delta beta depends on the metric, and the mass distance information actually comes from independent observations. So what event horizon telescope data, what we have for M87 star, so the ones that are highlighted, these are from the EHT collaboration. We have this angular diameter for the M87 star, that is 42 plus minus 3. Also the axis ratio. So it turns out that for M87 star, the viewing angle theta naught is very small. Unfortunately, we are not, this is one object that has been targeted, and it is not at a very high inclination angle, it is just 17 degrees. So therefore, the shadow is nearly circular, and the axis ratio, the ratio between the major axis delta beta and the minor axis delta alpha is less than 4 by 3. Okay, so the main thing that is the angular diameter delta beta, that allows us to tell us something about the space-time metric. So that is 42 plus minus 3 microarc second. Now EHT collaboration has assumed, suppose they do all these simulations assuming the Kerr geometry. So in this, using GR-MHD simulations, people and the Kerr geometry, one can actually arrive at the mass of the black hole as well. So the mass reported by EHT is 6.5 billion solar masses, whereas by studying the motion of stars, the mass of the black hole is 6.2 solar masses. By studying the motion of gas clouds around this object, the mass is also constrained to 3.5, which is quite discrepant from the previous data. This object also has a very strong jet, and by noting the angle that the jet axis makes with the inclination angle, the rotation axis of the black hole, one can actually, so basically the rotation axis, the jet axis is believed to be along the rotation axis, and the angle the observer makes to that is 17 degree. Okay, and similarly, another thing is that the observed ring, there is a bright ring and there is a dark patch. So one can see that there is a dark patch which is smaller than the bright ring. So this dark patch is believed to be, if it is 42 microarc second for the bright ring, then the offset is, maximum offset can be 10%. Okay, so if we just reduce, we take 10% of 42 and we take it, subtract it from 42 microarc second, so then the dark patch can be as small as that. So what we can do is that we can take a conservative estimate of the shadow and we can take an optimistic estimate, which is 42 microarc second, and the conservative one will be 10%, maximum 10% smaller than that. For Sagittarius A star also, the dark patch is essentially like 48.7, but the error is very high here, plus minus 7, and the emission ring, the ring that surrounds the dark patch, is like 51.8 microarc second. Again, from the Keck collaboration as well as the gravity collaboration, the masses and distances are independently obtained. And the inclination angle, I have missed here, yeah, I'm sorry, the inclination angle is less than 50 degrees, so generally people take it around 46 degrees. So with all these data, we are now equipped to test the backgrounds, whatever, suppose we take some alternative theory of gravity and we imagine that these Sagittarius A star and M87 star are black holes governed by that theory of gravity, then whether we can constrain the model parameters from this data. So this is not immediately relevant. Okay, so this is basically the people later on in 2021, the more recent EHT papers have come up with the polarized data. I mean, they have studied these two objects in polarized light, and they found that there is a very, these are the lines of polarization, and that indicates that there is very well ordered magnetic fields are present, and that is common to both the black holes. So that will not tell us much about the background space-time. So the EHT data is consistent with the predictions of GR. That is the first thing, but then it also does not rule out other theories of gravity, and therefore, so basically what people try are two things mainly: the exotic compact objects like boson stars or Grava stars, and so these are various alternatives to black hole scenario, and there are also black hole solutions in alternative gravity theories. So we have Kerr solution also turns out to be a solution in alternative theories, and well, also we can have non-Kerr black holes which can explain these data. So a lot of work has been done in this direction, and Professor Sushant Ghosh and his collaborators, they have also done a lot of work in constraining the background space-time from the EHT data. So in the next few slides, I will be discussing two of our works where we try to constrain the EHT data, constrain the background from the EHT data. So this scenario is essentially, we consider the brain world scenario in which we have this Einstein gravity in 5 dimensions. Okay, so the gravity is there in the bulk, so gravity can permeate in the bulk, but all the standard model particles and fields are confined in the brain. So the bulk is governed by Einstein gravity, but we as 4D observers, we need the gravitational field equations on the brain. It turns out that by applying techniques of basically Gauss-Kodaji equation and the junction conditions, So the details again, I do not have the time to get into. This is the gravitational field equation for an observer in the brain. Okay, but we are considering a vacuum brain, and we also, because the cosmological constant is also very small, we can neglect these two terms. The S mu nu is the squared energy momentum tensor, and in the presence, because the brain is vacuum, therefore we are looking for vacuum solutions. So the first three terms vanish. The fourth term is the term which is related to the Weil tensor in the fifth dimension. So this term actually tells us about the, it bears the signatures of higher dimension. Now this basically, this is like the energy momentum tensor, so it will satisfy this conservation of grad mu d mu t mu nu equal to 0, and it is also like the, so because it is coming from the Weil tensor, therefore it is inherently traceless. So this is very much similar to the energy momentum tensor we encounter in the Reissner-Nordström scenario, Einstein-Maxwell theory. Therefore, the black hole solution also, it also resembles the Reissner-Nordström metric if it is spherically symmetric, and the Kerr-Newman solution if it is axially symmetric. Note that this charge in Kerr-Newman solution is always positive, so because it comes as a square of some charge. But here in this case, the tidal charge which is inherited from the extra dimensions can be positive as well as negative. So if we get a positive charge from our center, then the positive charge will, we cannot distinguish it from the Reissner-Nordström case. But if it is a negative charge, then actually it is a true signature of higher dimensional, this kind of a brain world scenario. So this particular plots, these are essentially some of the theoretical shadow plots. The main thing I would like to emphasize is that, note that if we have a negative tidal charge, it is expanding. In all these four plots, if we have a negative tidal charge, it expands the shadow, and if it is a positive, it contracts the shadow, and the black one is the general relativistic scenario. Okay, so the various observables, once again the angular diameter, the axis ratio, and delta c. We can't probe much into the space-time from this delta A, delta c data. The main thing is the angular diameter. So here, basically we see that there is this, the data tells us, so we take independent measurements of mass, inclination, and the distance, and we compute the shadow. So this tells us, so these are basically constant contours of the angular diameter. The black one is 42, which is what the EHT tells us, and plus minus 3 is 45 and 39. And the spin of this object is around 0.9, that is from the jet power. So if we just draw a vertical line around 0.9, which cuts at 42 and 45 and then is 39, we see that this entire region, 42 plus minus 3, is better explained by a negative Q. But I told you that there is this offset of 10%. The black region is actually much smaller compared to the brighter ring. So if we take that conservative estimate, then the Q equal to 0, which is the GR scenario, that is very much included. So that is, so that is probably the reason. So here actually this, I told that this negative Q expands the shadow, right? And also the shadow, so one can get an expanded shadow either by increasing the mass or by increasing delta beta. A negative Q increases delta beta. So if we take a mass of 6.2, which is from an independent estimate, then we get this 42. The other option is that if we do not have this provision of a negative Q, which is what we have in GR, the Q is 0, then the mass has to be increased to get the 42 plus minus 3 microarc second. So that is why presumably the whatever EHT, the EHT people tell us that this mass is 6.5, which is slightly more than 6.2, what is measured from the stellar dynamics measure data. Yep. I'll just finish, take one more minute. This is not a very strong constraint. The Sagittarius A star data is actually not that, it is not a very good data, because particularly the accretion, there is a lot of, the variability of is much more in the flux for Sagittarius A star. The accretion, the matter is flowing very fast, and therefore the image is also quite blurred. So 48.7 is the conservative estimate, that is the dark patch, and one can see that this 48.7 microarc second data is explained by a positive value of Q in this case. But positive Q is also incorporated in the brain world scenario. But positive Q also can be there in GR if we take a Reisner-Nordstrom black hole. Yeah, and then the more optimistic estimate 51.8 if we take, then that is that there is a marginally negative Q, but of course the Q equal to 0 scenario is very much within the error bars. And also the error bar 48.7 is plus minus 7. So actually we cannot say it is anything very strongly about this background spacetime from this Sagittarius A star data. Okay, so basically these are from different mass and distance, independent mass distance estimates, and the results are more or less similar. So I would conclude with the first thing is that the HT data, although we are trying different alternative theories of gravity, it is very much consistent with the general relativistic predictions. But if we take the brain world scenario, then it turns out that the 42 plus minus 3 microarcsecond for M87 star is actually explained by the negative Q, but this needs, and for Sagittarius we require a positive tidal charge to explain the data, but we need more data, and in future EHT will be coming up with broadband images of these objects from 3 millimeter to 0.87 millimeter, and there will, the next generation high event horizon telescope is also planned with more observatories and more antennas in each of these observatories. So that will increase the resolution by a factor of 10, and then we will see what the data we can try to work in these directions here. So I thank you all for attention.
Thanks, Indrani, for a wonderful talk. So again, 2 questions I can take. Yeah.
Yeah, I have a very basic question.
Yes.
So, how exactly is the inclination measured for the black hole or observed?
Yeah, so the inclination for this particular object, okay, so when you are trying to, in general it is actually measured from the velocity. Yes, inclination is generally measured from the velocity profile. Okay, if you study the motion of stars around this object, but for these objects, particularly M87 star, there is a strong jet. Okay, it is believed that you're probably familiar with the Blandford's-Naik mechanism, right? The jet is powered by the black hole spin. M87 star actually turns out to be a very highly spinning black hole. So the jet axis is aligned along the direction of the spin. If that is correct, then the viewing angle, that angle, whatever we are seeing, that turns out to be 17 degrees. Okay, for Sagittarius A star actually it is slightly more uncertain. So from in order to fit the data, also this the X-rays, the data in X-ray radio, as well as the images, for consistent fitting of all this, one requires an inclination angle less than 50 degrees for Sagittarius A star. Yes.
So, you require a strong jet for the...
A Sagittarius A star jet is not yet confirmed, but it also has very ordered magnetic fields. The recent EHT data tells us that from the polarization data, it has very ordered magnetic fields, and people often say that there might be a hidden jet. M87, there is a strong jet, yes.
Thanks.
There is some, even for both the black hole images, there is some amount of polarization has been seen.
Yes, yes, yes.
Okay, so does the modified gravity can tell something about it?
Not directly. Actually, polarization, it is more related to the nature of the accretion flow. So from the polarization data, if I go back to that. 100%, which this one? What is?
This thing is that only 10% of the light they see is polarized, not everything.
Yes, yes.
So
yes.
I'm just wondering whether it cannot be only because of, all the explanations cannot be because of the jets. Or
no, not only the jets, there is also matter swirling around these black holes, right, the accretion flow. So that there is also, so from these organized polarization directions, one can try to map the corresponding magnetic field around these objects. So the magnetic, actually for M87 star, there is an estimate of the magnetic field. It's right 1 to 30 Gauss magnetic field for this object. But this is more related to the accretion flow, the nature of the accretion physics polarization data. The background metric can be probed more from the this angular diameter, and also if we happen to get a black hole which is at a high inclination angle, because these images are nearly circular. So if you are trying to view, if we get some data in future which is viewed edge on, then there will be a deviation from circularity. So not only the size but also the shape of the black hole will tell us more about the background space-time. And also it will be useful for ruling out many models.
Yeah, a nice summary. What I don't understand, what is the assumption in underlying accretion disk? You know that when originally they do imaging, they also had considered accretion physics, as you also told. And accretion physics has a lot of uncertainties, viscosity, angular momentum, whether it is Adolph or Sakura-Suniev. So in this case, my worry is already there are uncertainties in the underlying accretion model. Now you are trying to predict modified gravity effect, extra dimension. So how to remove the degeneracy? And those uncertainties are much more than this, as you said, very small change.
Yeah. So yes, so this actually has been addressed by this by the EHT team themselves. So here, for example, you see this image that they see. The main thing is that this 42 plus minus micro arc second, okay, this is actually an effect of the background space-time. The uncertainty in the accretion flow is because so this bright region has shifted. So after 1 year they have taken the data. So this first data was released based on the 2017 data, the first image. Then after 1 year they have taken they have observed this object for one more year, and this 42 plus minus 3 micro arc second is quite stable. Okay, so the uncertainties in the accretion flow, that is shifting this brighter region by 30 degrees towards the I think in the clockwise direction, whatever turbulence is there in the accretion flow. And so also when these images were actually, people have considered GRMHD flows, and they have considered this SANE model. You have also discussed the SANE and the MAD models in your talk. So people, while they have generated these kind of images, considering a host of accretion flow models in also the SANE and the MAD model, so this kind of an image can be simulated by the MAD, because there is ordered magnetic field which is also confirmed by the polarized data. So the MAD models are actually more in accordance with it.
That's why I understand. That is why I'm asking, when you introduce eventually extra dimension effect, then your MAD, for example, again has to be redone.
Correct.
So that's where exactly, how are we incorporating when you are predicting in your calculation, in your modification?
See, the thing is there are two aspects. If I am considering, so that is why I have considered the conservative as well as the optimistic estimate. The optimistic one is the bright ring, which is 42 plus minus 3. The conservative one is the dark patch, that is the 10% offset. Maximum how small the shadow can be and how big it can be, that is the ring. Okay, so this is actually an artifact of the background space-time. What if, yeah.
So when you were discussing about this image, unpolarized one, you mentioned about that the size of the dark patch is around 10% of the bright patch.
Correct.
So why is it so? Do you set it like that, or you observe it?
Yeah, that is what you observe actually. So basically people have to use, so these are various image processing techniques that they use. So basically they try to model the so different kinds of, what to say, so that here they consider different, so you have to get, so this is what they observe, okay. So that there are these 11 EHT observatories, they give you the image, and then you have to, like basically it's like you see a part of the image from each of these observatories, and finally you get the full image by using different imaging techniques, okay. And they consider a host of imaging techniques. If you look at the EHT papers, they have discussed in great detail that what kind of techniques they use to arrive at this. Yes, so your question is that how are they getting this?
No, my question is that is there any physics behind it that it's coming out to be 10% of the between the ratio
between. This is what you actually observe.
Yeah.
The
so
physics is actually like, so basically this dark patch is attributed to this background metric.
yes.
Okay. So the physics is, suppose whatever physics you consider, that should be in accordance with what you observe.
Yes.
That
I
is
so
basically
this
the thing.
depends
So
on the background.
it depends. So
it
this
depends, right?
part mainly, the dark patch depends on the
The
background. The bright region can be, this is mainly attributed to the accretion flow. Whatever uncertainties
whatever
you have.
interaction you are considering.
Yeah, whether if you have a magnetic field, strong magnetic field, or if you don't have such a thing, then whatever the nature of the accretion flow, right? The
Yes.
advection dominated flow or the magnetically arrested flow or same model, whatever model you take, that will actually be more sensitive to this part of the image. So if actually GRMHD simulations generate a library of these images,
I see.
and that is fitted with this data, and then you arrive at the
final
angular
image.
diameter, and
Okay.
from there.
Thank you.
Okay, so I'm sure there are a lot of questions we can have after the tea break. So thanks again, Indrani, for a wonderful talk. So now we move to an online talk. It is by Li from Institute of Theoretical Physics, Center for Advanced Studies, China. He will be talking about dark side of black hole, interior structures and dynamics. So yeah.
Just mute the microphone. Yeah, mute everything there.
Recording in progress.
Okay.
Hello, Dr. Lee, can you hear us?
Okay, good. So can you hear me?
We can hear you. Can you hear us?
Yes, yes.
Okay.
It-
So
Okay.
yeah, so we can start now. So we have 30 minutes plus 5 minutes for questioning. So
Okay.
around 25 minutes, I will give you a sort of a hint that it's 5 minutes left. Fine.
Okay. Okay. Thank you.
Yeah, you can start.
Okay. 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 Thank you. Thank you for the invitation. So I first apologize that I cannot attend this symposium. I can only attend online due to the visa problem. But taking this opportunity, I should thank the organizer for inviting me to give to introduce our recent work about the black hole interior structure and the dynamics. Okay, so this talk is based on our recent work with my collaborators. So with Ronggen Cai, is the professor in the Institute of Theoretical Physics, Chinese Academy of Sciences, and many other collaborators, including many students. So this is the outline of my talk. In the first part, I will give a basic introduction and motivation. And the next, I will introduce our main result about the interior dynamics inside the black hole event horizon. Finally is the conclusion and the discussion. So if you have any questions, so just interrupt me so I can explain more details to you. As we know, so black hole is a very important prediction by Einstein general relativity. So a black hole is a region of space-time. So here the gravity is so strong, the nothing, including the particle and the light, can escape from it. So the first black hole solution was predicted by Schwarzschild in 1916. So this is the solution, the metric. You know there is only one free parameter in this solution, is capital M, which is nothing but the mass of the black hole. This is the spherical case for the vacuum Einstein equation. This solution is very simple, you see, but it contains two fundamental features of the black hole. So as you see here, when R equals to 2m, this component just vanishing. So this is the event horizon of the black hole, is just the boundary of the black hole in some sense. And as R goes to 0, the curvature of the space-time diverges. This is called the singularity. So the black hole is the intersection of fundamental physics, astrophysics, and cosmology since the last century. So many breakthroughs of the black hole was predicted from theoretical study, like the gravitational collapse, the black hole thermodynamics, the singularity theorem. So it changed our understanding of the universe. So more recent years, due to the development of the technology and the science, so the black hole, the theoretical prediction, so the existence of the black hole has been confirmed by experimentals and observations. So now we can not only listening the gravitational waves from the merging of two black holes, we can also see the image of the black hole in some sense. I think you already saw these pictures and learned a lot from the talk, the previous talk. And also from the proper motion of stars, we can know there should be a supermassive object in the center of our galaxy. So according to our understanding now, this is nothing but a supermassive black hole. But frankly speaking, what's the nature of black hole is still a mysterious. And the black hole, we know, is the window to the nature of black hole. Actually, to explore the internal structure of black hole and in some sense space-time singularities is very interesting and fundamental, and it can provide a better understanding of black hole physics, gravitation, and even quantum physics. As I just mentioned, so now black hole is a real object in our universe. So as a real object, like an apple, so it's nature to ask, what's the internal structure for this real object? So let me give you more motivation for the internal structure of black hole. So first, it's associated to the strong regime of the theory, I mean strong gravity regime. It can help us understand the strong gravity property. And second, we know if the singularity exists, it may signal the breakdown of the theory. Is the theory a problem? Moreover, we want to make a prediction, right? So that means we want a theory have a well-posed inertial value problem. So if singularity can form generically and can be observed, or if there is an inner Cauchy horizon of a black hole, the theory will lose predictive power. Okay? There are also many other important problems related to the internal structure of black hole, like the singularity theorem I just mentioned, and the cosmic censorship conjecture, and the black hole information paradox. Actually, since the last century, there are some progress has been made in understanding internal structure of black hole. The first one I just mentioned is the singularity theorem, proved by Penrose and Hawking. It tells us, so the singularity typically occurs inside any black hole whenever some energy conditions are satisfied. independent of the symmetry of the space-time. So it means the singularities are generic phenomena in gravitational collapse, and the black hole formation is a robust prediction of the general theory of relativity. However, it does not provide any detailed description of the dynamics near the singularity. Almost at the same time, the BKL, they studied the dynamics near a space-like singularity. They showed that actually in many cases, the dynamics near the singularity is described by an isotropic chaotic solution of the Einstein equation. So more precisely, the space-time near the singularity is homogeneous and has a Euclidean metric, like here, that depends on some time, depends on time. T is the proper time, okay? This has this Kastner metric. You see, there has some 3 exponents, P1, P2, P3. They are not independent. They satisfy the Kastner condition here, okay? And you can show at least one component should be negative. That means some direction will explode up and some special direction will contract. So it's very complicated behavior. And then it showed that this BKL singularity can be understood from the cosmological billiards. That means the dynamics near the space-like singularity can be described as a billiard motion in a regime of some hyperbolic space. So the Hamiltonian text like this. H0 is the kinetic term, and capital V is the potential term from the curvature, from the non-diagonal component of the metric, and even from the matter field, the last one. They call the walls. That means the alternation of different Kastner universe is caused by the beam-bound boson due to this wall. But this formalism seems not applicable when the interaction of matter content becomes very important. I will show you some examples later. Okay, let's go to our work. So first, let's consider the eternal structure of this kind of theory. This is an Einstein theory coupled with a Maxwell field and a charged scalar field. This is the Lagrangian. So F is the field strength for the U1 gauge field, and the psi is the charged scalar field with a charge Q. And the capital Z and the capital V are the coupling functions and the potential. So let's consider black solution with some symmetry. So this is a hairy solution with the scalar hair and the U1 charge. Okay, and the topology of the horizon can be planar, spherical, and hyperbolic. The reason is that here the coupling Z and V are very generic. Okay, so we don't need to impose any specific form for these functions. So that means the geometry is quite generic. It can be asymptotic flat, and the theta, or other geometries. Okay, if we turn off the electric field, the gauge potential, and we have the Einstein scalar theory, our result applies to this simple case. So let's focus on the generic case. So our question is to ask, is any eternal structure or eternal horizon in this kind of black hole? So in principle, we can solve this black hole by these equations of motion. Okay, so in principle, if we can find the solutions for this system, you can see if there are any inner horizon inside the event horizon. But unfortunately, you see this system is the nonlinear coupled equations. We don't have any analytical solution, but you can try to solve it numerically, but it's case by case. So our strategy is to give a general proof based on this dynamics. Okay, the idea is as follows. So suppose besides the event horizon here, there is an inner Cauchy horizon inside the event horizon. This is our coordinate system. The singularity is that z goes to infinity. Okay. So have this picture, we know the Plenary function, GTD, should vanishing at both horizons. And meanwhile, we know the derivative of this function f prime is given by this one, should be negative at the event horizon. And the derivative at the Cauchy horizon should be non-negative. So this is the generic feature. And meanwhile, to have a smooth space-time near the horizon, so the gate potential should be vanishing for the charged scalar black hole. Then the key observation is that, so the system is like here, it's complicated, but you can construct a quantity we call the Q. It depends on the matter field, the metric, and the topology of the horizon. It seems complicated, but you can show that this quantity is radially independent. That means the derivative with respect to the radial coordinate is 0. That means Q is a constant. So since this is a constant, we can evaluate this quantity at both horizons, right? So you can find this relation because F is vanishing, so it can simplify. So this quantity, you can see the right-hand side of this quantity. So based on our assumption, so this should be negative. Okay, this part, because we have this kind of properties. But on the right-hand side, so when K is the topology of the black hole, so for the spherical case, K equals to is positive. For the planar case, K is 0. That means the right-hand side is non-negative. This, you see, this is negative, is non-negative. That means there should be no inner horizon for the spherical case and for the planar case. Okay, but for the hyperbolic case, K is negative. Okay, so both sides have the same sign, and we cannot exclude the possibility for the inner horizon for the hyperbolic black hole, but we can show that there only exists at most one inner horizon with non-zero surface gravity. And we can indeed find some concrete example for the hyperbolic black hole. Besides the event horizon, it has one inner Cauchy horizon. Okay, and actually our discussion can be generalized to many different cases. For example, for the nonlinear electrodynamic black hole, I mean here the electronic part is a nonlinear function of the field strength, and it can also conserve the quantity like this. And you can show there is no spherical and planar black hole, I mean the inner horizon for this kind of black hole. And more interestingly, if we use more constraints like the non-energy condition, you can have an even stronger result. Actually, from the equation motion, you have this combination, and this is nothing but the non-energy condition. That means if we want the non-energy condition is satisfied inside the black hole, this combination should be monotonic, right? Because it's positive. But meanwhile, we see if there is an inner Cauchy horizon, the gate potential should be 0. So that means the inner horizon is not possible if we consider the non-energy condition. Actually, the idea can also be generalized to the theory with vector here. For the vector here, because the vector can choose one spatial direction, the space-time is now anisotropic. Okay, but we can also use a similar idea to construct a radial conserved quantity to exclude the possibility of the inner horizon for this even more complicated case. Okay, so far we showed some no inner horizon theorem for some generic theory, but we can ask more. Can we give a more general proof without giving any form of Lagrangian? So the result is yes. So our starting point here is the Einstein equation. So this Einstein equation, and T mu is the energy momentum tensor. We know in the classical level, there should be some constraints on this momentum tensor called the energy condition. Okay, for example, this energy condition has been used to prove the singularity theorem, and for using the no energy condition or strong energy condition. So this energy condition, I think maybe most of us are familiar with this energy condition. Actually, for the strong energy condition and the non-energy condition, the physical picture is very simple. It means matter is attractive. Okay, this is our main result. Here we consider the static black hole. That means there should be a Killing vector, the time-like Killing vector. Then we can show that. So if the Einstein equation and one of the following three conditions are satisfied, that means the horizon is compact and the strong energy condition is satisfied, or the horizon is non-compact, but the system has hyperbolic or planar symmetry and the non-energy condition is satisfied. Or the third case, the horizon is non-compact, it's a two-dimensional surface, but this area scalar curvature is non-positive and the non-energy condition is satisfied. We can, in general, prove that there is at most one inner horizon inside the black hole. Since time is limited, I can basically show you the main idea for the first case. So for the static black hole, we have this kind of metric, right? So suppose besides the event horizon, there is two inner horizons inside the black hole. We have this regime, the shaded regime. And that means this red line is the space part. And the Killing vector is vanishing at both boundaries. And you can show that from the Einstein equation, you have this kind of combination. The capital D is the covariant derivative along this red surface, is a space manifold. And this part is a special space part, because HAB, the space part of the metric, this is non-negative. And this one, we can show is nothing but the strong energy condition. That means if the strong energy condition is satisfied, I mean this derivative, I mean the the derivative of n squared is the Lapse function is non-negative for along this red curve. Then, according to the maximal principle, that means the maximum of n squared must be at the boundary, okay? But in our assumption, at the boundary, you see c squared is 0, that means n squared is 0. So that's contradictory to the fact that c is time-like. Then we can exclude the possibility for the second event inner horizon. Okay, now let's move on to the interior dynamics inside the black hole. So as we know, this is a very complicated problem because inside the horizon, the dynamics are in the nonlinear regimes and the behavior should be sensitive to the detail of the model. Let me show you a simple example. We consider free charged scalar, okay, the very simple coupling. You see inside the horizon, the matter field, the psi, has some oscillation, and the metric has some exponential collapse. And after, when we go to the singularity, we have some plateau here. This is called the Kastner metric I just mentioned at the beginning. And there are also the alternation between different Kastner universe. You see, even for this very simple case, the interior dynamics is very complicated. Here, we can show that if we can ignore the potential term, okay, we can find that the interior dynamics can be obtained analytically. And if we change the coordinate, the metric like this is nothing but the Kastner universe I just mentioned. But here we have the scalar here. But to have this Kastner universe, we said the kinetic term of the scalar dominant system that have this kind of constraint. This is a very generic result. It applies to very generic potential
like the average function, like exponential form. At least we can check our analytical prediction analytically. So if for this combination, it goes to a constant, that means a Kastner universe. You see for different choice of potentials, it goes to a Kastner universe. However, if we consider a more complicated potential like this exponential form, you can show this constraint will break down at some particular position, so determined by this space-time dimension and the coupling and this parameter. And we can numerically show that indeed, you see this Kastner universe, and then there is a transition to a different kind of Kastner universe if we turn on this exponential form. If we have a larger coupling, so this behavior, it can be even complicated. You see, it has some bounce behavior between different Kastner universe, and also seems some periodicity in some studies. Okay, so you can see, you can find very interesting dynamics inside the black hole, at least based on some specific models. And at the late times, you can see there is a common feature, is the emergence of the Kastner scaling goes to the singularity. And depending on the interaction, you can see there are some bounds between different Kastner epochs. So a natural question appears. Can we classify the interior dynamics of the hairy black hole? I mean, analytically, not based on the numerical result case by case. The answer seems yes, at least based on our recent work. Okay, let's go back to the theory. So this is a general theory with a charged scalar here. So it's some couplings, and we focus on this kind of hairy solution. And we already showed that there is no inner Kersey horizon for this kind of solution. So now let's want to clarify the possible dynamics inside this kind of black hole. So to simplify our study, let's consider this kind of coupling, the exponential form. This is typically in supergravity and superstring theory. And we showed that we can have two typical analytical results. So this we show this plateau means the Kastner universe. And alpha is the Kastner exponent. In the first case, we can show that before and after the Kastner alternation, the component for this two Kastner universe, I mean their sum is a constant, determined by this coupling and the dimension of the space-time. And in the we call the Kastner transition. In the second case, okay, the exponent before and after the Kastner alternation, the product of their two numbers are determined by this combination. It's independent of the coupling, but fixed by the space-time dimension. Then, depends on these two typical Kastner alternation, we can classify the possible, Kastner alternations inside the interior of the black hole. Depends on the coupling kappa. When the kappa, you see, is large, this regime for the Kastner inversion and this regime for the Kastner transition, they have no overlap. That means when the Kastner exponent inside this red regime, there will be a Kastner inversion, then the component maybe go to the transition regime, then there will be a Kastner transition. If in this wide regime, that means if the Kastner exponent in this regime, the system is stable, there is no any Kastner transition or inversion, the system will stay in this Kastner universe. And actually, this behavior, this kind of behavior can explain almost all previous results in the literature, including the simple case I just showed to you for the free scalar case. And in the second case, it's a critical case. For this kappa, these two regimes just touch with each other. That means there is no stable Kastner regime. So when you sit down in this red regime, so an inversion, there will go to another Kastner universe, maybe in this transition regime, and it may goes back and goes to this one. So there's a never-ending chaotic behavior. And in the third case, it's more complicated. You see there are some overlapping. During this regime, both the dynamics play the important role, so it can give you very complicated behavior. So let me show you some examples. For the second case, this kind of Lagrangian can be obtained from the consistent truncation of M theory. And you see here, this is the analytical law predicted from our theory. And you see this exponent satisfies this prediction very precisely. And there is some transition, inversion, it's a never-ending behavior. And in the third case, I see there is an overlapping regime. Okay, let's also consider a typical example. This in 5 dimensions. This can be called from the type 2b supergravity. You see, outside this regime, so the law is given by our prediction. But in this overlapping regime, you see here, there is a very complicated behavior. It is non-Kastner behavior, okay? And you can show for a more generic case, for this kind of coupling, you see this plateau means Kastner universe. And you can see there's some non-plateau regime. This is the non-Kastner epochs. And this behavior should be beyond the cosmological billiards. And we should need a new theory to understand this kind of behavior. So it tells us that the interior dynamics is very complicated and interesting. We are not able to understand this behavior so far, so new theory or framework are calling for. So now let's conclude. So here we establish, a no inner horizon theorem for some kind of paired black holes. And we show the geometry near the singularity can be very complicated. And we can classify some behaviors, but we also showed some novel behaviors we don't understand. I think the take-home message is as follows. I want to convince you that a classical matter, it can promote the formation of event horizon that we know, but it also prevents the appearance of multi-horizons inside black holes. Actually, there are also many interesting questions we want to know and we want to solve. For example, to consider the more general case, other form of matters, like a vector field or some inhomogeneous case. And also, can we generalize our discussion to stationary case? Okay, also to understand the dynamics, in particular, different from the Kastner form. And so far, we consider classical gravity. It's also nature to ask, what happens if we consider quantum effects? Okay, so let me finish here. Thank you very much.
Thank you, Lee, for a wonderful talk. So let's have a couple of questions if anybody has questions. Yeah.
Okay, sorry, I cannot hear your voice.
Yeah, hello.
Hello.
So I have a question that you point out the no-Harry theorem. So from the no-Harry theorem, the shape of the event horizon. So the generally event horizon shape is a spherical. So if we are considering the Harry theorem, which you point out, what would about the toroidal kind of the structure of the event horizon?
You mean the event horizon?
Yes, toroidal kind of the structure.
But the event horizon should exist. We exclude the inner Cauchy horizon, not the event horizon. So we showed that for many kind of black holes, there is no any horizon inside the event horizon.
Okay.
That's our result. Because if there has an inner Cauchy horizon, we cannot make a prediction, right? It's a Cauchy horizon. So the general theory loses its prediction power. That's called the strong cosmic censorship. The Penrose proposed that
if the black hole have the inner Cauchy horizon, this horizon should be unstable.
Okay, thank you.
Yeah, here we just show that indeed in some theory there are indeed no Cauchy horizon, so the strong cosmic flagship is satisfied in this space-time.
Okay, thank you, sir.
Thank you for your question.
I have one question. All your solutions are asymptotically flat or asymptotic ADS?
Oh, that's a good question. So here I mentioned, so our result is independent of the asymptotical geometry. You see our theory, the coupling, the potential is arbitrary. So it can apply to any asymptotical geometry, including flat and the theta, the theta.
Yeah, the
Very
reason,
generic.
yeah, I'll just have a follow-up question. So usually the ADM mass or all the other quantities which we can define is valid, or we can exactly define when I have asymptotically flat spacetimes. Now asymptotically non-flat, especially de Sitter, becomes very complicated. So I was wondering, how can you make a basis without actually defining any of these ADM mass, charge, and things like that? Thanks.
Yeah, I see. Yeah, so you ask the definition for the mass of the space-time, right? So ADM mass.
I didn't ask for the definition. So what I'm saying is, if I don't know whether it is asymptotically flat or asymptotically non-flat, then the definition, how do I define the mass, charge, and other things becomes very, it's kind of observer dependent. So that's what I wanted to know, whether you are doing everything asymptotically flat or not.
Yeah, I know your question. So actually, this is a different topic. Actually, the definition of this quantity, I think I agree with you, is still unresolved problem. But here, our result, we don't need to the definition for this quantity. So here, we just use this conserved charge, you see. This is not the ADM mass or the charge. So we don't need to define this quantity. We just showed that using this conserved quantity, there is no inner horizon. But your question is not related to this proof. But yeah, the definition of this quantity is, in particular for the theta case, is complicated. But for the anti-de theta, I think it's clear. We can use some holographic renormalization. We use a counter term to define this quantity. Yeah, okay.
Thank you, sir. Very good talk. But I just had a basic question that the Cauchy horizon comes like from mathematical, like when it stops being globally non-hyperbolic. So how did you get that condition that if prime is greater than 0, like from the PD, like how did it came? Like that oil valued initial condition non-existence implies that. So could you just say? Thank you, sir.
Sorry, I did not catch your point. Can you speak again?
Yeah, so I am asking that for the Cauchy horizon, where is the initial value problems stops being like well defined, how did you get the second criteria, like the f prime is greater than 0? So maybe it is a basic question, but so how does that imply?
You mean this one?
Yes. So how does that imply?
Yeah, so suppose you see this solution is like this here, right?
Yes.
Okay, so we know for the event horizon, this quantity should be vanishing, right? Is the definition for the event horizon, right?
Yes.
And so if we have the inner horizon, that means this function f should from the below go so up, right? It should be another field for the Cauchy horizon. You can think from Penrose's paradigm.
Oh, okay. So I cannot see why it is Cauchy horizon as such. Like, I mean, it is a.
You mean why we call it a Cauchy horizon?
Yeah, why it is stopping initial value problem. Yeah.
Okay. Yeah. This we should go to the Penrose diagram. Okay. You see, you consider rational neutron black hole or Kerr black hole. You can think about the Kerr black hole. Or let's be rational neutron is very simple. It's a static black hole. We consider rational neutron black hole. So you can imagine its Penrose diagram. You see the first inner horizon is the Cauchy horizon. You can imagine the Penrose diagram for the rational neutron black hole. You can understand this feature.
Okay. Thank you very much, sir.
Thank you.
Yeah, so if there is no more questions, let's thanks Lee again.
Mhm.
Thank you, Lee. And yeah, we are now going for a tea break. So yeah, thank you for attending and giving this talk.
Thank you very much.
Thank
Okay.
you. Thank you.
Thank you.
Okay, so we'll be back by 11:50 or 55. Mean like try to be by 11:50.